Okay, so today I'll talk about the groups of the Stern model. So in the Stern model, which is one of the successful theory, and it will not be too much wrong if we say this is the only successful theory of particle physics, and that has been experimentally verified so far. So in the standard model, which is proposed by Glasso, Weinberg, and Salam, uh, so we will not talk about the field theoretic aspects of standard model, and that will be covered up in the particular discourse. But what I'll try to give an idea mostly on the symmetry point of view. Now, in the standard model, we have two different kinds of symmetries. One is like the space-time symmetries, and another is the internal symmetry. So, internal symmetry by means basically you can think of like an abstract space where the symmetries are disengaged and so on. So, what is gauge symmetry? Maybe all of you are familiar with this thing, but in this course, actually, I'll briefly introduce what is the concept of base symmetry, the global symmetry, and why we are called the internal symmetry, and so on, and how they are related with different kind of charges and quantum numbers. So the first thing that I want to introduce, which we have seen already, you are already familiar with, is the Lorentz group, and that's why I prefer to start with this one. So the space-time symmetry here, then this is we are working in the 3+1 dimension. So of course this is like a Lorentz group you can think of, and it's a non-compact group which you write it down as like SO3+1, and it contains actually 6 transformations. So it includes like 3 rotations, which are actually parameterized by or you can think of it as SO3, and then you have 3 boosts. And we have already discussed that how rotations being unitary and the boosts are basically non-unitary. And on top of that, when you put this translation, and that leads to a 10 parameter group, which is an extension of the Lorentz group, which is known as the Poincare group. And you can think of like a Lorentz group as a subsymmetry or subgroup of the Poincare one. Now, when we talk about the free Maxwell equations, to check, they are basically invariant under the 15 parameter conformal group, which is like SO4, 2, and which contains the Poincare group as well. But conformal group doesn't contain any dimensionful parameters. So, we talk about the massive fields mostly, where the particles and all the things have the masses. So that massless theory will not be too much relevant for us. So we restrict ourselves to the Poincare to start. So now, what are the Lorentz and Poincare groups? So SO3.1 contains 6 antisymmetric generators in mu, which satisfy the commutative relations like M mu and M alpha beta commutator. You can see there's a metric and then there's one of the generators. In this way, you can write it down. You can actually prove this thing if you know how to construct this M alpha beta. And this is here the M mu alpha takes with the values from 0, 1 to 3. And in the metric, in the signature, I am using here the diagonal -1 +1 +1 +1. So minus plus plus plus, that's my signature. So of course, if you want to work with this minus plus minus minus, yes, then you get the end product will be the same, but internal treatment will be different, and you have to be careful about that things like that. You don't mix the metric signatures. Now they act on the space-time coordinates x mu as x mu going to a mu x mu, where a mu is antisymmetric. That means this is a mu minus of a mu, and then it defines some kind of a length square, which is slightly different than the concept of Euclidean length. You can see there's a different signature here, and that reflects the non-compactness of this kind of group. But under the Lorentz transform, this is invariant. So you can take the commutator of a mu and a sigma, which is proportional to x, and matrix is there. Now, since the quadratic invariant is basically hyperbolic, this transformation cannot be represented with the Hermitian generators acting in a finite dimensional space. Okay, so then that's an open surface kind of thing that you think of. That's why the Hermitian generators in the finite dimension that we have like for example, like SU2, SU3, and they're the compact and the generators of emission, but where the generators are not emission. Now, all India representations of non-compact groups are basically infinite. That's very, very important thing. And possibly, when you have gone through the character and all those things, so possibly you have promised to talk about the non-compact characters, and there the main problematic thing while constituting the character something like those group or like similar kind of non-compact group is that the India representation of the non-compact groups are actually in dimension. And we will see if there's an description how to deal with that thing or realizing that non-compact group in terms of the in terms of the product of the compact groups and in terms of their character whether we can write it down in that non-compact. Now SO4 you can think of as like a product of SO3 plus SO3 and it's like isomorphism. So if there's a translate the non-compact case by defining Mij as epsilon I to jk and M0I to be the ki. So that's the mu actually encompasses the j and k rotations and the boost. Now the other conventional relations among the rotations and the boost that seen already. The important part is the ki commutator is not k, but when to boost commutator equal they don't need to kind of boost. Another important part is the boost rotation commutator is not zero. That means basically in which order they are appearing or you are using them, that actually alter the end result because they do not commute, they are not really independent. So whether you are boost first, then the rotation or vice versa, they are not exactly. Now, so 3.1 splits into two sets of commuting generators, which are basically half Ji plus I Ki, that is small IH transformer 3, and each of them satisfies this SO3 relations. So note that Gi plus minus Ik are not Hermitian unlike the compact case. So we have the under parity, you can think of like a xi going to minus xi, and this ji is going to minus ji, ki going to minus ki. So you can define some kind of parity operation here, which will take from one SU2 to another SU2. So now this you can think of like representing gi as sigma by 2 and ki as I sigma by 2. So then you're left on the so just to clear, these are not Hermitian like the compact case means the Gi and the Ki's are not Hermitian. Now here we can define the select kernel object psi l, which transforms like psi l prime and it becomes I sigma by 2 omega I plus I mu I psi. So this is transformation under the rotation and that dictates the transformation under the push. So now you can see because they do not commute, so you cannot just split it out. Right? Now psi l is a left-hand wild spinner. So we have already discovered what the spinners and all those things. So you should be familiar with this kind of already. So psi l is the left-hand wild spinner which transforms like 2.1. That means it's actually two-dimensional under the one of the SU2 and single the with the other one, and psi r is the vice versa of that. And psi l and psi r are attributed to each other by this parity kind of properties. So here the psi r transforms psi r prime as e to the power I by 2 sigma I omega I minus I mu I psi r, and psi alpha if you think of it like 2.1 psi alpha dot to be 1.2. So about these dotted underline indices we will talk about more when we talk about the square helicity combination. Now this psi l goes as like sigma 2 psi r star, which is like a conjugate representation. Okay. Note that this E plus ID, which stands for like a SU2 adjoint, and then singlet under the other SU2 and E minus ID is singlet under the first SU2 and adjoint under the second SU2. So it's like a magnetic, and we'll see when we talk about the gauge bosons or the vector bosons, so they basically will see that they are transferring on the adjoint of this question. So now here the X mu P nu commutator is basically I beta mu.
And then m mu, basically x mu p nu minus x nu p nu, which are basically giving the orbitals environmental kind of thing. And s mu is the kind of a spin part. So this doesn't have any classical analog. And then for psi n, we have this Sij is less than ijk sigma k by 2, and S0 is basically sigma I. Now the Poincare group is nothing but the Lorentz group plus the translation, which you can think of as the momentum, linear momentum. So like a S mu going as S mu plus n, where n is the constant. So you can take up the commutator like m mu p sigma, what you can write it down in this way, and p mu take 2 commute, and p mu can write it down in terms of a del del S mu, and then S mu divided by that using this metric reason what this is. So that Poincare group can be thought of, it's like a Lorentz group and then a semi-direct product of the abelian translation. So this actually symbolizes a semi-direct product. So now we can characterize this by two Casimir operators. So one is PU, and other is WW. So PU, this is the mass square, and W is basically the Pavlov-Dumansky operator, which you can write it down as a half epsilon mu sigma P nu in rho sigma. And if you take the commutator of WW, you get this minus I epsilon mu rho sigma P rho W sigma, and this P nu and W nu are there after each other, and that will independent. Now, we can have multiple choices for this P nu P nu. So, for example, let's say if you start with minus m squared, or m is a real quantity, that means it could be minus m squared is less than 0. Okay, P nu is a time lag vector, and that's from the STR. So, by Lorentz transformations, we can go to the rest frame at P0 equal to m and Pi equal to 0. So, that actually tell us that W0 will be 0, Wi will be minus m Si, which is basically minus m by 2 epsilon ijk sjk. Okay, which is the generator of the SOC. And Si is a commutator of the CI epsilon ijk spin because it's the SOC, so the structure portion of the and the quadratic Casimir is basically s square, which is the eigenvalue s into s plus 1, where the s can take the value of 0, half, 1, 3 by 2, and so on. So we have this P mu equal to m square, the mass, and W is m square s into s plus 1, which is basically spin. So now we can do a different representation, which is called the Newton-Wigner representation. The idea is to represent generators on an initial surface in space-time. So identify with x0 as physical time, such that the initial surface is the slice of space-time and the x0 equal to constant. So you can take x0 like a trajectory and you can slice that space-time point, and then in practical slice that trajectory will hit in a single point, and you're fixing that. So that's x0 equal to constant. And then your W0 in that the temporal part of the Pavlov is basically half epsilon ijk pi sjk, and Wi can literally expect. The Lorentz generator split into space notations Mij that don't affect the initial surface. The spatial notation, they don't affect the initial surface. And the boost M0I, which actually into a temporal part. So they will have a more complicated expression on the initial surface. To find it, we say that S0I equal to A epsilon ijk Js. So we have to find out the A. And then we calculate this WW, and we can write in this particular structure. And once we manipulate that thing, we can find this particular form that A equal to 1 by P0 plus minus M. So as initial time x0 is fixed value, the conjugate variable P0 is minus I del 0, which is no longer well defined because the x0 is a fixed quantity. Now, which can be dealt using the method of Lagrange multipliers. So what we do actually, we define a P0 tilde, which is basically P0 plus lambda P nu plus M square. And now choose lambda to eliminate this P0. If you do that, then you find that the P0 tilde equal to plus minus square root of Pi plus M square. And this is the positive and negative of the solutions. Now at x0 equal to 0, we obtain the Newton-Wigner representation of the Poincare generator. which are basically PGO tilde CC plus minus M square minus del I del I. But Pi equal to minus I. Okay. Now Mij you can write it down as like from there the way we define the MV, from there we can define the Mij, and which take this I, it's like you can think like power thing. So Xj del I minus Xi del J plus Xi is plus P. And M0 is basically minus half Xi commutator and minus this Xi del J sk, where there is A that you have calculated. So note that Xi and P that don't commute. So the generators on the initial surface X0 to 0 split into dynamical generators. One is Pi and another is the Mij. And dynamical generators, the Hamiltonian PGO tilde and the boost M0I, which move the system away from the initial surface. This is the purpose of boost. So here we define a state in the Hilbert space. The pointer group acts on the Hilbert states, which are basically labeled by these quantities, which is the thin momentum, mass, speed, and the magnetic momentum. This is the way we define in this particular representation the state vector in the Hilbert space. So now we can think of another representation, which is known as the light cone representation. So Dirac introduced the front form, in a different way of expressing the dynamical equation. The initial surface is light, that means the S is moving 0 and labeled by constant values of x plus as 1 by 2x0 plus x3. Now for fixed x plus, its conjugate variable p minus is 1 by p0 minus p3 and s plus p minus commutator is minus I is no longer well defined and must be expressed in terms of the remaining variable, that is x minus and p plus. What is x minus? 1 by 2 x0 minus x3 and p plus is 1 by p0 plus p3. Okay. So your x minus p plus commutator is minus I. And the transverse variable xa and pb that satisfied basically your xa pb commutator is I delta A for A equal to 1. Now there are 7 kinematical Poincare generators here. P plus, PA, MAB, M plus A, M plus minus. The latter is kinematical at x plus equal to 0 since it contains x plus p minus. Now there are only 3 dynamical Poincare generators. The light cone Hamiltonian P minus tilde and the 2 boost M minus A we have. So now using this Lagrange multiplier, the previous case, we can have a well-defined P minus tilde, which is PA plus M square by P. The remaining 3 transition generators are P, there P plus and P I. They are basically here MAB equal to XAPP minus XBPA plus SAP. That generates a transverse Bell notation. Now we can write it down as P in this particular form and determine the P is M square. So now in the rest frame of the particle, this matrix reduces to M times the unit matrix as in this way. But you people write down in this particular frame. So this is the matrix that transforms the rest frame into the light control. But the Park-Dubrowski can be given in this way. And from there you can define W plus, W minus, and W by K transform Y. We have this coordinates and epsilon 1 to the basically this antisymmetric density. So further we find that S plus A equal to 0, M plus A equal to S plus P plus PA minus XAP plus, and then S plus minus equal to 0. Once we set, then we find out that M plus minus equal to minus X minus by P plus X plus P minus and equal to minus X minus P plus at X plus equal to 0 initial surface. So we can evaluate S minus A from comparing the entries in the W1 plus and W2 on both sides, and also for the W minus, and which is that S minus A Hamiltonian material. We said that TA equal to MSA and T1, T2 commutator will become I M square S1. The light cone representation of the Poincare generators are P minus tilde equal to this, P plus tilde is this, and so on the set of generators. So here, the Hilbert states are labeled as P plus PA, the light cone momentum, the mass, spin, and position of the magnetic. So now we have the different case of the spinning P equal to 0. So this is the case which is basically effectively the previous one with m tends to 0. Now the W is basically now like. So your P mu and W mu are like and orthogonal to each other. So in the light frame, the P tilde minus, the P1 tilde, P2 tilde to 0. And so the W minus and W1 W2 equal to 0, W plus is given like this. The W plus P tilde plus equal to S12, which is defined basically nothing but a helicity, which is the SO2 generator. Now in the light form representation, that TA of order transform as the transverse vector. And you can write it under S1 to T1 commuters, T2, S1 to T2 minus T1 and T1 to T2 commuters. Now, if you set TA equal to 0, the Kate vector is P plus PA m equal to 0 lambda. It's a massless particles of fixed helicity. Okay? And the values of lambda are fixed by the group, not by the algebra. Now the exponentiation of the transverse rotations must be single value that requires the helicity to be plus minus half or integers. This case represents a massless particle with a single value of helicity lambda. For example, 0 plus minus half plus minus 1 so on. Now from the point of group theory, these massive representations can be thought of as sum of massless equivalents. That's very interesting feature. For example, if you think like a spin 1 representation, they have these 3 states of magnetic components, minus 1, 0, 1, each of which occurs as a massless equivalence. That's it. Now, if the TA is not equal to 0, in this case, T are simply the C number components of transverse vector. The state is realized as TA acting on this P plus PA psi A equal to psi A P plus PA psi. Here, psi A is the transverse vector, such that W is psi A psi A. And here, helicity is no longer a good quantum number, as the light cone boost, which contain Ti, change the helicity by 1 unit. So hence the representation is made up of an infinite number of helicities spaced by 1 unit. So thus we have two distinct representations depending on whether the helicities are integer or half integer. They are called the continuous spin representation by the Fourier, and no interpretation actually they are in terms of the particles. Talk about the helicity more when we talk about the helicity. Right. So now I'll introduce briefly about the case because we will do this theory in the concept of quantum thinking, but I'll discuss very briefly which will be relevant for our course. So here we have the concept about the global symmetries. Where you see phi of x, which transforms into I alpha phi of x, and where the alpha like a phase or continuing one rotation. Now we can think of like a complex field phi I is Lagrangian density between these factors. So where the phi I transforms into alpha phi I, where the alpha is a number, it's like global fields. So more genetic structure would be like phi I x goes as phi I prime x equal to omega ij phi j x. And so omega ij actually is arbitrary SUN matrices. And these transformations such that the norm in the fixed space, which is defined as the phi j star phi j or the phi star prime phi I prime, that remain basically infinite. So that tells you that the phi transforms like a e to the power I theta I ta, that is the phi. Here was with the SUN generators and going on from from a equal to 1 to this n square minus 1. Now these TAs are basically your n square minus 1 number of normalized generators where the SUN, and they are basically TATB commutator is given as IFABCTs. Now how do they transform under the SUN plus SUN? So if we have this field phi, which has two representations R1, R2, and this let's say consider this R1 is representation under the SUN and R2 is the representation under the SUN, then phi can be having these quantum numbers. So then phi transform under this like transformation under the SUN, this part, and this will be like transformation under the SUN part. So this change is answered from 1 to n square minus 1. This is very for generators n square minus 1 and so on. And these are generators, okay, that actually suit the ion dimension representation of a single dimension, and similarly T tilde are the generators which actually follow and constructed based on the which represents your one, for example, the application. So for the parameter transformations are global, that is do not depend on the x and t, but let's consider theta as theta x and then the kinetic term is no more invariant, that is del mu phi star prime and the del mu phi prime. They are not equal to del mu phi star times del mu phi. Because once you act the derivative act on these parameters, del mu theta will no longer change. So we need to modify the Lagrangian. For example, let's say phi of x, both phi prime of x, omega of x, phi of x, and omega of x, let's say belong to SU2. Then del mu phi prime of x will be omega del mu phi plus del mu omega phi. The prescription is to basically, going from del mu phi to d mu phi, such that the d mu phi prime equal to omega d mu phi. So that the way field is transformed, okay, same way the covariant derivative must transform, and that's the origin of this construct of the covariant derivative, such that d mu phi prime is transformed like in this way. So here the mu goes to the mu prime, and which also fix the transformation of the mu prime, such that this we can ensure. And so the new Lagrangian is basically this part is almost the same, only the derivative part from ordinary to goes to the covariant derivative. Okay. And now this is remain invariant under this phi going to omega of x, phi of x. What are the gauge kinetic part? So the f mu, this is f mu prime, it transforms as omega f mu omega inverse, such that the trace of f mu is also remain invariant. The f mu for non-abelian gauging SUN gives in this way the A is the gauging base here. So the omega is basically 1 plus inverse transformation, you can think of 1 plus I ta theta x. These are the generators, they are the parameters of this transformation. And here note that the trace of TATB for N delta again is the normalization of the generators. In case of SU2, the dimension is given as 2j plus 1, and the normalization for given any dimension d out of constant out of spin j given as nj equal to 1/3 j into j plus 1 to j plus 1. And in general, the normalization is proportional to the DT level. In general, normalization is the half of the. So yeah, and the important part is the structure constant, which are given as a proportional to the trace of TA commuted with the TVTC. Now for this, when TA J1 I1 TA J2 I2 is given as a delta I1 J2 delta I2 J1 minus 1 by n delta I1 J1 delta I2 J2. This will be a term. So this is all about the symmetry part, and once I use more representation oriented standard model, so I'll discuss more about this.